Simon Josey, as part of replacing our original plan, has agreed to give a short talk on the Irminger Sea. I'll just go ahead and turn it over to Simon.
Yeah, thank you very much, Dan. And so 2 days ago, Bablu told me that Penny was dropping out, and so I said, well, I can give a talk if you'd like to. So I got my chance to advertise a poster, but also go a bit further than that, because Bablu said, well, you better put some ideas in about where ACSIS is going next, or what would be questions for ACSIS going forward. So as well as a bit of stuff which may be a bit parochial for you on the Irminger Sea, I hope you'll keep attention to the end, where I'll talk about what I think are a few more issues as we go forward. So I'm going to talk briefly about measurements from a mooring in the Irminger Sea. We've never had these measurements before, so they're extremely exciting for us. And relating those measurements to an atmospheric forcing feature here, which is relatively small scale, a tip jet from the tip of Greenland. And then I'm going to relate that to some large scale modes of variability that you've probably heard of, the North Atlantic Oscillation and the East Atlantic pattern. So let's orient ourselves. This is a plot I've used at the start of most talks now, where this shows time running from hours up to centuries on the bottom, log plot, and then the surface net heat flux. And these little ovals are supposed to represent different processes. They're not all the processes, they're just some I'm interested in. And we're down in the first part of the talk here, looking at tip jets, which cause very strong heat loss, 400 to 800 watts per square meter, additional heat loss from the ocean on time scales of hours to days. Many of you will have heard me talk about the cold anomaly in recent years, or the big blue blob. So in particular, strong winters, we can have heat loss of 50 to 100 watts per square meter over several months. You may also be aware that we measure at rapid ocean heat transport across 26 North, and there's been a decline in that heat transport, or people argue there has. And if you look at that over decadal timescales, and that averages to a signal of about 10 watts per square meter. And then, of course, I hope all of you are aware of the fact that if, as a result of anthropogenic climate change, we have a global warming on centennial timescales, and that averages to about a ½ watt per square meter. So the signal we're most worried about from societal perspective is actually the smallest one on this plot. So in my title, I put Forgotten Sea. Let me just tell you why I think it's a forgotten sea, and this is based actually on a nice review by Bob Pickard in a book a few years ago. So this guy's Fridtjof Nansen. They explored this sea around about the 1910s, 1915s, and this is the location of the Irminger Sea. And he suggested, based on his measurements then, that this was a region of deep convection. And then for various reasons, primarily because lots of the subsequent observations took place in the Labrador Sea, which is this region here, attention switched there, and people thought of the Labrador Sea as being the main side of convection, tend to forget about the Irminger Sea entirely. Now, recently, as we've just heard from Bablu, we've got a lovely set of observations developing on these OSNAP lines. There are moorings in the Irminger Sea, both the surface ones that I'm going to talk about, but also deep moorings as well. And there's definite evidence now for deep convection. A nice paper led by a colleague of mine, Femke de Jong, in Oceanography a couple of years ago. And we also can have this context plot, which Bablu showed, doesn't come out that well here, which shows that a lot of the variability is apparently occurring. This is in the transport and on the eastern part of the basin, and that includes the Irminger Sea, and not much in the western part, the Labrador Sea part. So the Irminger Sea is of interest, and it's also of interest because of these atmospheric tip jets. So hopefully I speak for everybody in this talk, because it's got a bit of atmosphere and a bit of ocean. So if we look here, we see that Greenland, of course, has a rather elevated terrain with the glaciers there on the orography. And what happens is these primarily westerly and southwesterly flows slam into this mountain barrier, get forced up, and when they descend the other side, they accelerate and they form a jet. So there's been lots of research on that. There's a nice discussion of the dynamics in a paper in Tellus about 20 years ago. That tip jet comes out of the ocean, out over the ocean. Thought wow, this must be what you need. Is some of these moorings have been in the tropics for 20 or 30 years now, but it's actually very hard to maintain them in the strong wave conditions of the high latitudes. And so we've had this one in place, and I should say all the credit goes to colleagues at Woods Hole, so led by Bob Weller, who put this mooring out. I've had no involvement with the deployments. I just get to use the data because I'm fortunate, and it's located at this position off the tip of Greenland, which the colours show is a region of very strong heat flux variability. So we now have information from this mooring over 5 winters now, in fact, and I want to stress it's in a data desert. I call it the subpolar desert. I started my career trying to develop flux fields from ship reports, from meteorological reports. Each one of these little dots is a ship report, one report from a ship, which enables you to estimate the heat fluxes from the wind speed and air temperature, etc. And each of these are different months. This is December 2015, February 2016. And although you have, it looks good down here, you've got observations down here, you can do something there. It's guesswork here. We have no idea what's going on in this region. We've known more about the moon being topical in the last 50 years than we have this particular location from direct measurements. However, we now have those measurements, and here are some of them. There's another time series which should be on here for last winter. So here are the first 4 deployments. You can see quite often that the mooring falls over in winter, but we do get into winter. It's deployed in summer, and usually it's disappeared in February or March some years. This year, I think it's still there now, but we do have enough observations to look at variability from winter to winter. Just look at this one, which is the net heat flux, and we can see very strong losses in winter 2014-15 and weak losses in the subsequent winter. And we've been asking ourselves, why has that happened? And trying to relate it to the tip jets and trying to relate it to atmospheric modes. Here I'm trying to do that in terms of the North Atlantic oscillation, which you will know about, and the East Atlantic pattern, which is just a measure of blocking or the absence of blocking in the eastern subpolar giant. So first of all, the North Atlantic oscillation, historically that's been thought to influence the tip jet currents. So when you have a strongly positive NAO state, you have lots of storms impacting on Greenland, you have lots of tip jets. And that's borne out by the observations. In our first winter, that strong heat loss winter, we had 12 tip jets in the month of December, and the NAO index was a strongly positive value, 1.6. However, in the following winter, the weak winter, we only had 3 tip jets, and yet the NAO was stronger still. So in this paper, which is in GRL, I should say, we answer why this is the case, because the classical thinking suggests we should have strong heat loss then, we should have strong tip jets, but the classical thinking doesn't think about the second mode as well. And in the second mode of variability in that winter was particularly strong. It's incredibly strong, an index value of 3.1, which basically means there was no blocking. And in that situation, with very strong low pressure system on average there, and we argue that what's happening then is it sets up a stronger, what's called a barrier flow. That's been explored by my colleague Kent Moore in Canada, the strong barrier flow which suppresses the tip jets. So we only have tip jets when we have a strong NAO, but not outcompeted by a strong East Atlantic pattern. Now that's important because we're trying to understand the sparse historical records of hydrography in this region, which say that we've got convection occurring intermittently over the last 60 years or so, very sparse indeed. And people have been puzzled as to why we don't always get convection when we have strong NAO conditions. And I would argue if we go back and look at the record again, and we take this second mode of variability into account, we can get a better understanding of that. Just to try and convince you a little bit further, I went to ERA 5, so the latest ECMWF Preanalysis product, and I took out in the years following 2000, all of the winters with relatively strong NAO conditions, so NAO greater than 1. We should be getting strong heat loss in all of these winters in the classical picture, but that is not the case. If you stratify it according to winters where the NAO is strong and stronger than the East Atlantic pattern, then we do get the strong heat loss expected. The blue bars there, this is the heat loss in any given winter. And then if we look at the conditions where the NAO is strong but weaker than the East Atlantic pattern, doesn't happen that often, but you've got 3 bars there where there's virtually no heat loss at all. So that's supporting the picture we've developed. And if we look at the large scale picture, at the large scale scheme of things, so if you just do a simple composite under these 2 conditions, NAO strong and stronger than the East Atlantic pattern, well, then we have a classical picture. Here's our classical NAO, winds are coming like this, and we've got lots of tip jets forming. If, however, the East Atlantic pattern dominates the NAO, then we get a broader low pressure sail here, we get a stronger flow along this coast, and we're arguing that's what's crossing out the tip jets, that's what's suppressing them. So if you want to know more about that, read the GRL paper or look at my poster. But now I'm going to skip over the movie, so I'll try and play it just so I'm saying it. So of course, we always want to connect observations with models. Here's a 100-year or part of a 100-year couple of model runs that we've been doing in Southampton. This is the ACSIS run, so 12th degree ocean, N512 atmosphere, and it just shows wind speed in that top left plot, so we can see lots going on. and we can see the occasional tip jet forming. Here's one isolated here on a particular day in the model. So we've got these strong tip jets, and of course we want to use the model to explore some of the mechanisms we've developed so far from the observational analysis, and we will be doing that. Right, I don't want to stand between you and your coffees, so I've rattled through that a little bit quickly. But here's the bit of philosophy that Bablu asked me for. So I'll just put a couple of points in here, which are the first ones to come into my head. This is the last slide, by the way, which come into my head as things we could be thinking about, which we may want to bring up in discussion sessions. So we've heard a lot already about, is the Labrador Sea still important? You'd think reading Susan's paper, the Lozier paper, and from an OSNAP perspective, we were wrong. The Labrador Sea is not important. It's all occurring in the Irminger Sea and the Eastern Gyre. Well, I don't quite go that far. I think there's obviously, and Bablu's indicated that as well, there's obviously a strong role for the Labrador Sea, and we need to ask ourselves how strong. And then I was very interested to see this paper a couple of months ago in GRL by Leon Shafiq, who I've got to know reasonably well. And this one actually says, is it the Nordic seas? So the Nordic seas is this region up here. So for people not familiar, this is the Nordic seas. Here we are in the subpolar region, in the Irminger Sea. Here we are at the Labrador Sea. So in this paper, by virtue of the fact that they estimate a heat loss value here of about 270 terawatts compared to 130 there and less than 100 there, they're saying all the action's going on in the Nordic seas. Now, I rarely hear the Nordic seas mentioned in ACSIS meetings, and I think another thing, that isn't criticism, by the way, it's just observations going forward. We need to make the connection between these different basins and really get a better picture of what's happening in the different potential deepwater formation sites. Are they key to the state of the MOC, as these people claim? Next one, timescales. I've gone on and on in previous meetings about the importance of looking at particular winters, because the 2013-14 winters and 2014-15 winters had extremely strong heat loss, and I argue that those are a large determinant of the fact that we had very cold temperature anomalies in the North Atlantic at that time. I think that's a reasonably strong result at the interannual timescales. But the very interesting thing to do is to now marry that understanding with what's going on at interdecadal timescales, all the fabulous work that John and Rowan and people have done, and also looking on to centennial timescales. So I wrote a review of some of this stuff recently in annual reviews of marine science. And of course, if you go to 100-year timescales, then we have the warming hole that people argue about. So for those who don't know, if you look at global warming and you subtract it out of the temperature change, then you actually get an anomalously, it's not cold, it's not anomalously weak warming in this same region of the subpolar Atlantic. So this region here, and that's work led by people like Stephen Dryfield in Southampton. So how do we marry that knowledge of what's going on at 100-year timescales with the AMV discussions we've been hearing about Atlantic multi-decadal variability, which kind of reach out to those timescales as well? Are they completely independent? Can you just remove it as a trend, or is there some interplay between the two? That's another thing to think about. And what I should say, this is my kind of a slightly provocative slide. It's on my poster. So this is the figure which Rowan showed earlier on in his slide, but a slightly different format. So this is the 2006 to 2015 trend. And I argue that you have to be very careful where you take your end year because of this strong interannual forcing. If you chose 2013 instead, you would get this figure. And if you chose 2014, you get this figure. So looking vertically on here, this is the change in the end year. And looking horizontally, it's a change in the beginning year. Come and look at the poster, I'll show you more. But I say, when looking at decadal trends, we need to be very, very careful about what the final year is. I've also talked about small-scale processes, tip jets. Are they important? How do we go from the small-scale processes to some of the regional processes which we've been thinking about? And then finally, I've got one. This is one of my favorite slides, and it's from a paper by Alexander and Dessa, a lovely paper written in '95 about reemergence from the ocean. So the idea here, for those who don't know, this is the atmosphere-ocean interface. I've added some color to the original black and white. This shows strong heat loss in one winter. That creates a cold signal in the ocean. As the winter turns into spring, the top layers of the ocean re-stratify because you've got heat coming into that part, and the cold signal can get sequestered below this now shallow mixed layer. Come along to the next winter, and you only need normal heat loss, and when you get your deepening of the mixed layer, this signal can come back. That's reemergence. We're going to hear a very interesting talk from Bablu later on about what happens when you have that reemergence, and it can impact on the atmosphere. It can influence the subsequent state of the NAO, it can influence European climate. So I think that's something we need to be thinking about as well. So that's my philosophical slide. I hope Babyl's happy with it, having pressed me to do it. And I'll stop there and we can have some coffee.
Great.